Okay, so let's go ahead and get started. Okay, so let's go ahead and begin. So before I forget, I want to mention, and this was in the same email that I sent when I was going to teach this morning, about how this Thursday, the lecture is going to be on the control unit. In fact, the next two lectures are going to be on the control unit hardware. And, that's the most challenge, well, in my opinion, and I think a lot of other people that teach this class, in their opinion, that's the most challenging part of hardware to design is the control unit. So that's why there's two lectures. So, all lectures are important, but I think the control unit lectures are particularly important. And like I mentioned in the email that had new scoring, the beginning of Thursday's class. So right when you come in at 3:10, there's a graded in-class activity. Okay, so you want to make sure that you're here on time, just like today. I was very impressed today. I got to say, all three of my sections, everybody was here on time. I think that's the first time that's ever happened. Okay, so like I said, I wish there was a midterm every day so people would be here on time every day. I know you don't wish that, but I wish that. But I don't want to grade a midterm every day, so we're not going to do that. But anyway, for those in-class activities, you have to be physically present to get credit. So get here on time Thursday, so you get credit. And also that activity is important for the control unit that we're going to start talking about that. Okay. All right, so today's class, I'm going to say a few more things about the registers in the reg file. That's why I put a handout. Oh, wait, does every table have a handout? Oh, okay, there it is. I was just looking up there. Where's the handout? I thought I put one there. We talked a little bit about, the different registers in the reg file, but we're going to talk more about their alternative names and their uses. And then we're going to go into what are called assembly directives. Okay, these are instructions directly to the assembler, even before the program is assembled. And then I'm going to show you how you can put data into the data segment of real memory, because remember that there's the three segments in real memory, right? You got the code segment. What's in the code segment? The instructions, right? That's where the program is, right? The instructions. And then you have the data segment. Right, and then top of that, you have the stack. Now, the stack segment we won't talk about until we get to subroutines, which is the very last lecture at the end of this month. So it's like 2 weeks away. But what we're focusing on today, after we talk about alternative names, reg file and uses, and also some assembler directives, is how you put data into the data segment and also how you read data from the data segment. And the data segment, just like the code segment, and the stack segment for that matter, is organized in byte addressable, just like we talked about the code segment, right? 32-bit, organized in 32 bits that are byte addressable. Now the code segment starts at address 0. Remember, our first instruction is always at address 0. Does anyone remember, or you can look it up, what the highest address of the code segment is? What did you say? Close. Yeah, you got very good. Yeah, 5 F. Right, that's your range for the code segment, right? From address 0 all the way up to address 5 F. Okay. So what that means is that the data segment the data segment starts at 6,000 hex, right? This is all in hex. And to tell you the truth, I don't remember what the top address to the data segment is, but I could look it up on the same sheet that has all the other range. Okay. But you're going to see, knowing that the data range starts at 6,000, an address of 6,000 hex, that's important. Okay, so anyway, we'll get to how you put data into the data segment and how you read data from the data section. But before that, there's just some things I want to go over that have to do with the reg file, particularly their alternative names and their uses. So first of all, and we already talked about this, there's 5 special reg file registers, specialty registers. One of them is register 0. What's the alternative name for register 0? 0. Very good. And why is it called register 0? The contents are always 0, right? Because you make it that way, right? You're hardwired. You did that when you designed the reg file, right? Hopefully. Okay. All right. Register 1. What's its alternative name? Stack pointer? Close. That's what register 2. Stack pointer or SD. So what's register 1? You look on the sheet. Return address. Yeah, RA return address. Now these 2 registers are important when we get to subroutines. Okay, so we'll come back to them when we get to subroutines. And also the stack, obviously stack pointer. We think that's something to do with the stack. Okay, but then there's a bunch of registers. I think there's like 7 of them. If you look here. Yeah, if you look at the bottom table on the page, T0 through T6, those are the temporary registers. And T0 corresponds with register 5, T1 corresponds with register 6, T2 corresponds with register 7, T3 corresponds with register 28. Okay, they're all what are called temporary registers. And as the name implies, temporary registers store not, or they don't store. Better write it this way. Temporary registers are for, or are not for long-term data. Right? Your name implies that, right? Temporary. So things that we consider temporary are things like a loop counter. I remember when you were doing, it was a couple of assignments ago, you were doing a software where you had to have a loop. So, you count how many times, or use a register to count how many times you've gone through the loop. You would use a temporary for that loop counter. Also, like intermediate calculation. Right. Say you have a calculation with the number of steps, right? As you're doing the steps, you would use a temporary register to hold, after one of those steps before you do another step, let's say.
Are you actually talking about immediates? Like immediates or intermediates?
Well, immediate in an assembly language, immediate's a number, like in an instruction, Yeah. This is just like an intermediate, like in between where you begin and where you end. Yeah, in fact, it's funny you mentioned that because last class I said intermediate, but I wrote immediate because I was thinking immediate because, we've been using that term quite a bit, right? A lot of the instructions have here, but yeah, this is just, in a process between where you begin and end, you're doing steps. And after one of those steps, you may want to store where you're at before you do the next operation. So you would use a temporary register for that. Okay, and then save registers are for long-term data. Examples of what we mean by long-term, like addresses, results, input data. Okay, those types of things. is what you use the save registers for. And again, if you look at the bottom table on this sheet, you can see that there's 12 save registers, S0 through S11. S0 goes with register 8, S1 goes with register 9, S3 goes with register 18, and so on. And then there's, let's see, how many A registers? And then there's 8 what are called function argument registers, okay, the A registers. And those are for subroutines. Okay, so we'll come back and talk more about these registers when we get to subroutines. Okay. Now, the reason I bring this up at this point is because for software number 5, that assignment, which when I'm done here, you'll have enough information where you can do that assignment. For software number 5, we want you to use the alternative names. So no more using like X with a number like you have been doing. You would want to use either a temporary or save, put either the T with the number, the S with the number. Now, for software number 5, if you were to mix these up, like if you were to use a temporary for long-term data and a save for, short-term data, you're not going to be marked down. Okay, but we at least want you to get used to using, the alternative names. Now, the only other software assignment there is the software final, final project. And in that final project, you also are to use the alternative names. And there, if you use, something that's not used in the right way, like you use a temporary for save and vice versa. And also by that time, you'll understand when to use these function argument registers. There, you could be marked down. Okay, but for software number 5, if you mix these up, you're not going to be marked down. Okay, we just want you to kind of start getting used to using it. Okay.
SR stand for store register.
No, that these function arguments are useful when you have subroutines. So sorry, yeah, this is subroutines. And again, if I ever use an acronym or a abbreviation and I'm not sure, by all means, let me know. Okay. All right. So any other questions on these alternative names and their uses before we move on to some assembly directives?
So you'll actually like type the alternative name into the RARS program?
Yeah. In fact, we'll get to some examples like here. Now, you haven't seen this instruction yet, but we'll talk about it. But yeah, see S0 instead of, I think it's X8, right? I think S0 goes with register 8. So instead of putting register X8, we put the alternative name. Yeah, and see, the main reason for these alternative names is to give some standardization, if you will, to the programming, right? Because if people use these registers for particular uses, now the program becomes more mobile, right? So that's the primary reason. And again, it becomes particularly important with subroutines.
What is a pointer rate?
Oh, that's good. We will get to that when we get to the stack point.
Okay.
Yeah, that's coming on. We gotta save it till we get here. Okay, so let's talk about assembly directives. And as I have written, assembly directives are like instructions to the assembler to take some action. So this occurs before the program is run. And these directives are not instructions. And because they're not instruction, directives are not converted to machine code. So they're, it's no machine code. Right? Because, your instructions in your program, when the assembler takes that, it turns it into the machine code, right? Each of the instructions, the 32-bit machine code that you can see in the assembly manual under each description, right? Detailed description. But these assembly directives, they're not instructions, and therefore they're not generated into machine code. Now, there's a number of these different directives, and the ones that are important for this class we'll go over. The first one is this. Now, this is a dot, okay, period, dot EQB, okay, which is short for equivalent. What you can do with this directive is you can make numbers equal to a word. Okay, so like here, you can make the word switches equal to this number. And where this is beneficial is that it can make your code more readable. For example, we've done this, right? We've done load, immediate, and then we've had a register, like X5, and then we put the immediate, which, this is the address for the switches that we have. So, we've been doing like this. Well, if you have this assembler directive before where your code is, instead of writing this number, you can just write the word switches. Okay, so it just substitutes, a word for some value. And again, the purpose of it is just to make your code more readable. Okay. Now, here's a directive .text. This is the default. And this is what you've been doing, right? Because up to this point, when you typed into RARs, you've only typed instructions. So there was no need to tell the assembler that you had instructions because it defaults to that, right? If you don't put anything, it's just going to take whatever you put in as an instruction, okay? But you'll see in a moment if we're defining, or if we have a directive that's, a data directive, which is this right here, this .data. Well, you'll have to put in this .text and tell the assembler where the instructions start, right? Because typically you'll have this directive, this data directive first, and then after that you'll have your program. So where the program starts, you got to put .text. Okay. Now .data, the default word. Okay. But you can specify what the data is also. So you could specify if it's a byte, by just putting .byte. You can specify a half word with .half. And you could also specify, a word too, if you want to, although that's the default that we just talked about. But you can put .word.
So when you type that in, would it be .data space .byte?
Actually, in the examples that I'll show you just the example in a minute, you could have these on separate lines, or you could separate. Oh, well, yeah, if they're different, they got to be on separate lines. But you'll see that sometimes, like you'll have multiple of one of them, and in that case, you can put commas between them. Okay, but you'll see in the examples that are coming up. Okay, right now, it's just that if you have this data assembler directive, and you'll see that this is how we create, or this is how we, put data into the data segment of the real memory. And then we can, once we have the data in there, we can then read from it. Okay, so I think this will become clearer once we do some examples. Okay, in fact, that's what's next, some examples. So let's get rid of this real quick. All right, so let's look at this example here. Okay, so we start off with the directive.data. And then you can see we follow it with a .byte, and this is the data here, 23 hex. And then another .byte and data 10. And then a .half, data 25 hex. And then a word, .word, data 100.
It's hex 23, not more than a byte.
Hex 23. Well, let's see. This would be 4 bits. This would be 4 bits. So a byte's 8 bits. So it's okay.
But it's 2 bytes. Oh wait, a byte is
See this? Yeah. See, this would be. Remember, you can go from hex to binary by writing each hex character as 4 binary bit. So you see, this would be 0, 0, 1, 1, and this would be 0, 0, 1, 0. So yeah, it's 8 bits, but you know, it's good that you're thinking that way, right? Because that's something you do have to think about, right? That this can actually fit into a byte. So, okay. So what this is going to do, well, before we actually say any more about this, let's come over to here again. Because as I said earlier, this data segment of real memory, it's byte addressable just like the code segment, right? And the stack is also byte addressable. So remember what we mean by that. Since it's byte addressable, this first byte of the data segment has address 6000 hex, right? And then this next byte is going to have address 6001 hex, right? This is going to be 6002, 6003, 4, 5, 6, 7, 8, 9, 10. Whoops, 10 is not that in hex, right? What is this in hex? A, B, right, and so on. B, D, E, F. Right, we could keep going.
So wouldn't it be 0 on the next line? Or 1, 0?
Oh, 1, 0, you're right, sorry. Yeah, because this would be F over here. Right, 1, 0, 60. Thank you for correcting. And this would be 1, 4, right, for 20. This would be 1, 8. Is that right? Yeah, 24. Okay, but coming back here, whatever you put after the data directive, it's gonna put that at address 6000. So you see, this would put this data at address 6000. It would put that hex 23 right in this byte right here. Okay, and then this byte would go to address 6001. Okay, it would put that 10 right here in this byte address. Okay, then we have a half word of hex 25. Well, it would put this it put that data, the 25 hex, at address 6002. Right, so you see, remember a half word is 16 bits, which is 2 bytes. So it would put that data in these 2 bytes. And then this word 100, this would go at address 6004. Right, it would take this whole, excuse me, it would take this whole row since it's a word and word is 32 bits.
It's not gonna get theoretical enough for the cell in empty. Let's say you pull one and you pull half and you pull half. We'll go 0, 1 to 1.
Okay, so you're saying this is still a byte?
Yeah.
All right, so it would be 6000. What's this? A half word with 6001 is the
Yeah, sure.
okay, so that would use these two.
And you pull half again, you
Oh.
right?
Okay,
3.
okay, it's a good question. So let's just make sure everyone's on the same page. So yeah, the first was a byte. The byte would be here, address 6000. If the next was a half word, it would take these 2 bytes. Now, if the next one's a half word, what's going to happen is, remember, you cannot cross a word boundary in real memory, whether it's the code segment or the data segment or the stack segment. It's all the same, that you can't cross a word boundary. So if you tried to do a half word with this address 3, it would try to put a byte here and a byte here, but the hardware won't allow it to happen because it's not designed to allow a crossing of a word address. So, you know, like in RARs, you know, just like if you are trying to either load or store, you know, in the code segment, like an instruction load or store, and you cross a word boundary, RARs is not going to like it. It will spit out some sort of error message. Has anyone seen that error message yet? Has anyone made that error and seen it? I don't know what it specifically says, but it won't like it.
Never got it.
What's that?
Never got it.
Never got, yeah, I haven't either, but
Get it.
If anyone ever does, let me know. I'd like to see what it actually says. It probably says nothing to the effect of what's happening. It probably says, like most error messages, probably cryptic, but yeah, it won't like it if that happens. Okay, so just like in the code segment, you can have labels, right? We use labels for intermediates in our code, like for branch instructions and jump instructions. Well, in the data segment, we use symbols. Okay, but symbols in the data segment are just like labels in the code segment.
Wait, when you said, do you mean we use them for immediates? Because wouldn't the label for the jump instruction be an immediate, not an intermediate?
Okay, yeah, we're going back to this again. You're right. When it's a label and it's an instruction, the label is for immediate, which is just a number. When I wrote intermediate here, I'm just talking about like some step in between other steps. Yeah, it's nothing to do with like immediate. Yeah. But here what I'm talking about is now in the data segment, because prior to today, the only thing we were talking about was in the code segment, because we were just looking at a program made of instructions. Okay, so in the code segment, it's called labels. In the data segment, they just call it symbols. It's just a matter of semantics, really. I would imagine some people probably call these labels too, but technically they're symbols because they're in the data segment. Okay, so here's an example of some symbols. And you can see that, just like in this top example, after the data directive, we got a byte, we got a half word, and then a word. So, the addresses for this data is going to be the same as what we had up here. This is going to be at address 6000. This is going to be at address 6001. This is at address 6002. This is at address 6004. Okay, now if I put another symbol along with some more data, like I'm putting a byte here, byte of this data 50 hex, what would the address be of this byte? Because this byte is here, right? This byte is here. This half word is here. And then we got a word that's taking up these 4 bytes. So where would that byte of 50 hex go?
6008?
Yeah, 6008, right? Because this word takes up 4 bytes, right? Starting with address 4. So it's taking up all these bytes here. So this byte would be address 6008. And then if I put like a half word here, that half word would be at 6009 and 6008. Okay, does everybody see that? See, that's really probably the most important thing when you're dealing with the data segments, whether you're putting data in like what we're doing here, or whether you're getting data, reading data from, as you're going to see in a moment. It's just understanding how the addresses work. Okay. You got a question?
So we're looking at what is 0, 1, 2. There's a third number with byte coding on that layer. Is it possible to write through it again?
Possible to,
Right to that.
well, you could always, well, what we're doing right now is not writing per se, because writing is like like a store instruction, which, you can also do, right? You can store to the data set just using these addresses. This is like predefined before you get to your program. Like the assembler does this before it ever like takes your program and turns it to machine code and starts going through it, kind of thing. But you could like say well, let's say we put this data in, like for example, we put this 50 hex. We put the 50 hex into address 6008. Well, now in my program, I could store something there. Like I could have a store byte and put a different data here, like some other data, and yeah, it would overwrite it. Is that what you're questioning? Okay. All right, so now let's see how we would read data from the data segment. So this is getting data from the data segment. Well, look, there's this instruction LA that we haven't used before. And if you look at your instruction manual, right, which you should always do, right? If you see an instruction for the first time, to say, oh, what does that instruction do? Well, let me open up my instruction manual because it has a detailed description that tells me everything I want to know about that instruction. And if you open it up and you go to LA, this is a load absolute address of symbol. And if you look at the form of the instruction, this is the destination register, and this is the symbol. So it's going to take the address of this symbol and put it into this register. Okay? So this takes the address of the symbol and puts it into the register. Puts into register. So the address of this symbol, as we just talked about earlier, is 6,000. So this instruction is going to put 6,000, hex 6,000 into register 5. Okay, that's what that instruction does. And again, you just have to look at the description in the manual. Okay, now this next instruction you've seen before, or something like it, right? Because it's a load instruction. So you've seen like load word, load half word. I don't know if you've ever needed a load byte yet, but just like those other instructions, it's a load instruction where it has the destination register here, it has a source register here, and then this number out front is an intermediate or immediate. Sorry, you got me saying that now. All right, and you've seen this, right? I mean, what's going to happen here? Like, what's going to happen with this 1 and it's register 5? Yeah, it's going to take the contents of register 5, where we put the address of the symbol, right, where 6,000 is now, and it's going to add 1 to it, and then use that as an address. So you see, it takes contents of register 5, which is the address of the symbol that we loaded into that register, right? So there's 6,000 right here. It's going to add 1 to it, so we've got 6,001, and then it's going to use that as an address and put the data at that address into that register. So you see this puts data at address 6001 hex into register 6. And what is the data at address 6001? It's a hex 20. Right? So you see this would put hex 20 into register 6.
So it's not adding 1 with the contents of register 5, it's adding 1 to, oh, no, it is adding 1 to the contents, because it's the next address in the contents,
Well, in the data segment.
in the data segments. Yeah,
Yeah, because see, we put 6,000, 6,000 is the address of this symbol, and this instruction put it into register 5. Now this LB instruction is adding 1 to that, right? So 6,000, and then it uses it as an address, and it takes the data at that address and puts it into register 6. Specifically, it's taking the byte, right, with LB, and that's what we have at address 6, right? We have a byte of 20 hex.
The data at that address was conveniently a byte. If it was a word or a half word or a word, we still use LB on it and it would just cut it.
Oh, so you're saying like if when we were putting data into the data segment, like this is a half word
Yeah.
and it had the same address?
Yeah.
Okay, Well, then whatever that data in the half word was, it would use these 2 bytes. But if you do a load byte, it would just take that part of the half word. So yeah, I mean, that's not gonna cause an error or anything. Yeah, it would just essentially take the lower half of that half word. And you've seen cases where you might want to take like lower and upper half of something. Because there was an assignment where, it was a word and like the top half was one number and the bottom half was another number. So it's not inconceivable that you would do something like that. So, yeah. Okay, so any questions on anything up to this point? Okay, so now the next thing we're gonna look at is that sometimes you might want to allocate a portion of the data segment without initializing it with any data. See, all this that we're doing is, we're putting data in a particular address or addresses of the data segment. But you may just want to allocate a certain part of that data segment without initializing it with any data. And the way you can do that is with the directive dot space. Okay, so here's an example where you still have to start with dot data, because anything after dot data is going to involve the data segment. Okay, so if you're ever dealing with the data segment, you want to tell the assembler this first. Okay, well, this first symbol, see, here's the dot space directive. Okay, so dot space, and then you see the number 20. And I just picked the number, this could be some other number. But whatever number you put here, that's the number of bytes. Okay, that's the number of bytes that you want to allocate in that data segment, for something. Okay, well, how many words? Let's see. Let me write the question. How many words is 20 bytes equal to?
5 words.
Right, it's 5 words. How'd you get that?
Just divided it by 4.
Yeah, right, because there's 4 bytes in a word, right? So if you get 20 bytes, this is 5 words. So you see what this directive is going to do is that it's going to take 20 bytes in the data segment and essentially it becomes like a reserved spot where you can write data to. Now it doesn't specify any values. Now one misconception is some people think, okay, well, since I didn't specify, that means everything's going to be 0. But that's not necessarily the case. You don't know. I mean, there's going to be something there. There's always zeros and ones, right? It's not like not 0, not 1, right? It's either got to be one or the other. But you don't know exactly what it's going to be, right? It's just that you haven't defined it. Okay, typically when you do something like this, later on, like after you do some calculations, let's say in your program, you'll write to that part of the data segment. Okay, but that's the key difference between this dot space and what we were doing here. Here we're specifying the data that's going to a particular address in the data segment. Here we're just allocating a portion and not defining what the initial values are. So it's basically undefined until later we write to it.
What happens if you allocate like 17 bytes? So it's not like divisible by 4?
Well, you can allocate 17 bytes. It's just you're not going to have like an even number of words, or the words would just be 4 in that case, right? Because you have like 4 words plus a byte. Yeah, but yeah, you could do something like that. But I think it's more conventional that normally I would say this is going to be divisible by 4. Okay, so that being the case, what would be the word addresses? We got 5 words. So what's going to be the first word address? 6,000, right? Then what? 6,004. 6,008. 6,001. Right, 6,000 C. 6010. Right, so you see that would be our 5 word addresses. Okay, then I've got this other symbol, right? Symbol 2. And now here I'm actually defining what I want in this address, right? I'm saying a word with this data of 10 hex. So what's going to be the address of this here, of D symbol 2? It's going to be what? Yeah, it'll be 6,014. Right? Because our allocated space is 1, 2, 3, 4, 5. It's this block right here. So now if I'm specifying data after that, it's going to go in the next available word address, which is 6,014. Okay, so that's what this would go with. And then where would this byte be? 6,000, say it again? 18. Right, it would put that byte of 20 hex into this address here, this byte address. Okay? So is this all making sense? Because again, I think that's the most important part of all this is just understanding how the addresses work.
So so when it goes to the next address, it goes to it based on like how much data is taken up by like a byte, for example.
Right, well, yeah, like here, the reason this has to be 6,018 is because this word's taken up, 4 addresses, starting with this. So, yeah. So like, if you did a half word next, like say your next, here was a half word of some amount, some value of data. Well, that half word would be at 6,019 and 6,008
So if it wasn't
or
byte,
6,001.
so if it wasn't byte addressable, you like wouldn't be able to do the byte command on there.
Right, or you wouldn't be able to do a half word. Remember, that's really a big difference between the memory module and the reg file, right? Because the reg file is not byte addressable. So all your addresses are just word addresses, right? You got address for register 0, address for register 1, right? All the way up to register 31. Yeah, in order to be able to do like a load byte or a load half word or a store byte or a store half word, you need byte addressable memory. Yeah, if you didn't have it, all you could do is either load a word or store a word. So yeah, that's a good point. Okay, so one more example, and then we'll talk about assignment number 5, and you'll be able to start that today. Okay, so here's an example creating arrays and also loading from an array. So again, you start with the data directive. So here, this symbol array, we're just allocating, again, 20 bytes of the data segment. Okay, but then we're following that up with another symbol that I just, as you see, you have called array 2, where now we're actually specifying the data. So just like we talked about just a moment ago, we're going to have a word at address 6,000, or we're allocating a word at 6,000, 6,004, 6,008, 6,000 C, and 6,010. Right, so that's what this line gives us, right? Again, for these word addresses and these 20 bytes, we're not specifying what the data is, right? We're just allocating that portion of the data segment. But now this symbol here, array 2, I'm actually specifying the data. And you see, these are 3 separate bytes. Instead of writing like on each line a byte like I did here, you can do this. You can put it on one line. Byte with data 3, byte with data 7, byte with data 8. So what this would do is it would put a 3. Let's see, we've got a word at address 6,010, right? Fourth one. An allocated word here.
Wait, it's not already being used by the base. 2010
Right, that's, yeah,
But you started, so
exactly. Yeah, that's what I was just gonna. Yeah. Yeah, you're right. That it's these 5 words that are allocated due to the space, like you just said. So that 3. Right, that 3 would go in byte address 6014. See that 3 would go right here. And then the 7 would go into the next byte address, 6015. And then the 8 would go into the next byte address, which would be 6016, right? All right. So, 3 goes into 6014, 7 goes into 6015, and 8 goes into 6016. That all make sense? Okay, so see, that's creating what data we have in the data segment. Now, to read from array, that's when you're using the LA instruction along with, either LB or LW or LH, right? Depending whether you're reading a byte word or half word. So what this instruction is going to do, and again, this is your destination register, this is your symbol. Well, actually, I should ask you, what is this instruction going to do? Exactly. It's going to take the address of this symbol and put it into this register. And what is the address of array 2? It would be 6014, right? So you see, this is going to put address 6014 into register S0. And then what's this instruction going to do? Yeah, it's just going to put address 6000. So put address 6000 into register S1. Okay, how about this instruction, this load byte instruction? What's that? Yeah, right. This is going to take S0, which is our address 6014, and it's going to add 1 to it. So this is going to be 6015 now. And then what's going to happen? Say that again? What is it going to put in that register? Yeah, it's the data. Remember, it's the data at this address that goes into this registry, not the address, the data at the address, right? And 7 is the data at this address. So you see this puts the data at address 6015 into register T0. All right, so everybody see that? All right, so what does the load word instruction do? Well, what address is it going to use? What is it? Well, S1, it adds these, right? So it's going to use address 6008, take that data and put it into T1. Now, we didn't put anything in there, right? We just allocated it, so we don't know what's there. But whatever's there, that's what it would put into register S1. That's probably not like the best thing to do, right? Because we don't know what's there, but that's what would happen. You have a question?
As a reminder, RAR is just their number at years, the bulk of the decimal. So in 14 on the site, they just rescribe decimal value.
Well, I meant, these are all X. I just didn't write the 0x. But yeah, in RARs, if you didn't put a 0x, it would take this as a decimal.
Okay.
Yeah, so yeah, you want to be careful. I'm not being careful here. What's that? Oh, thank you. I just can't believe I never remember. And I write it right up there in two different places with an exclamation point. You would think I would see it, but I don't know, someday maybe. Okay, so I think you're ready now to talk about software number 5, okay? So software number 5, just like all the other software assignments, has 2 parts to it. And, you may recall that I've been doing one example in class and then you do the other example. Well, it's a little bit different with this one because I'm just going to get you started on the part that you're going to do in hand in, which is part 1. Okay, and this is what part 1 is, the problem statement up there. The reason I'm ignoring part 2 is because part 2 is basically a sorting problem. And based on, what programming language you've had previous to this class, it really, in my opinion, creates like an uneven playing field because, some people, I think, like the CPE majors, depending on, like what orientation class you took, you probably had, or some of you, not all of you, had like some C programming. And, EE students get a little bit of Arduino programming in their orientation class, which is based on C. But, EEs, unless you've taken that 1 unit class that they offer on C programming, haven't had any C programming. So unless you've seen like some sorting algorithms, part 2, it's very hard to come up with a sorting algorithm from scratch. What's expected in that problem is you look at some sorting algorithm that you've done in a previous class and just take that and, turn it into assembly language. So anyway, because I think problem 2 of that assignment sort of creates an uneven playing field, depending on what a person's previous experience with coding is, we're just going to do the first part. I'll get you started. Basically, I'll show you how you set up the data segment. And then after that, it's just writing instructions like you've done before. Okay, so as you can see in the problem statement, there's a sequence. Now, it's the last name of a mathematician from like the Middle Ages that was Italian. And I've seen different ways to pronounce his name. Some people say Fibonacci, and other people say Fibonacci. I don't know which one's correct. I don't know. Does anyone know Italian? Well, it's one of the other. But anyway, it's a sequence, and I guess this is a pretty famous sequence. I mean, I'll be honest, I never heard of it until I looked at this problem statement. But if you Google it, there's a whole history about the person, and I guess it's used in computer science quite a bit. It's used in the business world, maybe crypto. I don't know. But anyway, it's this sequence that starts at 0. Let's say go 0, then 1, and to progress in the sequence, you just take the 2 numbers, like the last 2 numbers, and add them together. So, like to get the next number in the sequence, we take 0 plus 1, 1. Then we take 1 plus 1, 2. Then we take 1 plus 2, 3. Then 2 plus 3, 5. Then 3 plus 5, 8. 5 plus 8, 13, so on. Okay, you just keep on going. And what we want you to do in this problem is to take the first 25 values of this sequence. Okay, starting with 0, and you'll end up with this number here. Now, what I would recommend is, if you decide to do this by hand, before you go any further, Google it and check your answers against, what it should be, just to make sure you didn't make a mistake somewhere. That will throw everything else off.
Couldn't we just like code a for loop to do that for us as well?
Well, you mean to get these numbers?
Yeah.
You certainly could, but we want you to use what we've talked about here as far as using the data directive. Because you're just gonna put these numbers into the data segment of real memory and then use your program, reading from that and. Yeah, but I mean, you could do what you're talking about, but it wouldn't go along with what we just went over, basically. Okay, so to get you started, you want to start with the data directive. Okay, because again, once you put that, now the assembler is going to put what follows into the data segment of real memory. Then go ahead and use a symbol now. Just like with labels, with symbols, you can use whatever word you want. Okay, and it's good to be descriptive, just like you've been doing, like with your labels and in your code. So here, what I did is I used the symbol sequence. Need a colon in that. Sort of like a label with a colon. Yeah, you got to put a colon with the symbol, just like with the label. And then we're going to specify the data as words. And then you can just list the sequence. So you just put like 0, 1, 2, 3, 5, 8, 13, and so on. So, it's going to put this 0 at address 6000. It's going to put this one at address 6004. It's going to put this one at address 6008, so on. Okay. So that's going to put the data into the data seg of the real memory, and then put .text so the assembler will know what follows is now your program. Okay, because if you don't put that, it's going to think this is also in the data segment, right? It'll probably come with all kinds of errors. Okay, so that's the part you have to do. You need to come up with the program that's going to do the rest of this, where it looks at your sequence and it takes, let's see, what is it? It calculates the difference between values that are 3 spots away from each other. So, we'll take like 0 and 2, calculate the difference. It'll take 1 and 3, calculate the difference, 1 and 5, and so on, until it gets to a point where there isn't a value. Okay. You can look at the full description here. I mean, I think I wrote most of it out. And then the other thing is you want to output the difference. Like for each difference, you want to output that difference to the LEDs. All right, so it's going to be like calculate the difference, output to LEDs. Calculate the difference, output to LEDs. So what kind of construct does that sound like? Yeah, you're going to do some sort of loop, right? Okay. All right, so with that, you have enough information. Now, as I have written up here, this assignment, Software 5, it's due a week from today. That's because Monday of next week is a holiday, so that's why it's not Monday, it's Tuesday. And then remember, as I talked about before the midterm, I delayed the due dates for the hardware assignments last week till after the midterm. So tomorrow, the ALU and the immediate generator is due. So if you don't have that done, that should be your priority. And then your next priority should be the branch condition generator and the branch address generator, because that's due Friday of this week. Okay. All right. Well, go ahead and work where you need to work. And Eric's here. Hi, Eric.